Welcome back, everybody. So, as promised, in this video, we're going to actually solve a differential equation from beginning to end. And this may or may not look familiar depending on your Calc 2 class as a prereq, but we'll step through the process in case we don't remember how this works or if there's any confusion, which just for completion, we'll go ahead and step through this process. So I do have a fully worked solution here in the notes, but I'm going to go ahead and start from the top. So let's see. Again, generally we can put our differential equations into the form dy dt equals f of t by y. So f is a function of both time and y of t. So generally, this is possible, and for many of the physical systems that we deal with, we set up our models intentionally so that they have this sort of form. So there's usually not too much trouble to make this happen. So let's walk through an example of how we might solve a differential equation, or how we might actually go through figuring out which functions solve this equation. And we'll go ahead and do this in general. Remember that we had our freefall equation here, minus mg minus gamma v. This was an equation that we've been using kind of as a our prototype of this is a model that we would like to find solutions to. So we're just trying to solve for this v function. And well, this kind of differential equation is a very general setup, or it has a very general setup. And we're going to go ahead and see what happens when we take that general form. So right now, what we're going to go ahead and do here is assume that we have constants a and b. They're just going to be real numbers, but right now a maybe not greater than 0, but it definitely should not be 0 in order for this to be at all interesting, right? Because if this was equal to 0, if a was equal to 0, then we would just have dy dt equals b, and that's just a constant. We can go ahead and integrate both sides and wind up with y equals bt plus an integration constant. No problem. So let's see the interesting case when a is actually equal to 0, or not equal to 0. So in this case, this is a particular kind of differential equation. It's what we call separable. And the way that we can make this easy to deal with from a numerical or from a computation standpoint is we can go ahead and divide both sides of this equation, so dy dt, by the right-hand side. So I wind up with dividing by this ay plus b. So provided that's not equal to 0, I can do this. And this will equal 1 on the right-hand side. Now, if I am careful, if I think about this guy in terms of a chain rule, or in Leibniz notation, I can technically multiply both sides of this equation by a dt. And when that happens, I can really think about this as two differentials on the left and right hand side. So in this case, I'm effectively pulling all the y's over to one side of the equation and all the t's over to the other. And once I'm there, I can go ahead and integrate each side respectively, right? Because this apparently the derivatives of the things we're looking for have to satisfy this relationship. And when we do integrate, on the right-hand side, it's not too bad. The right-hand side is very, very easy to integrate, right? I'm just integrating the one function. But on the left-hand side, I have to do a little bit of work. If I use a u substitution and say u is equal to ay plus b, then du is going to equal a times dy, and then the b differentiates to a 0. So dy I can replace with 1 over a times du. So that means that this piece becomes 1 over a du over ay plus b, and that is equal to, I've already integrated, a t plus c. So, oh, excuse me. The whole point of this is so I don't have to use that as the bottom. I can just use a u, because that's exactly what this guy is. So if I do that, that is a 1 over a times the integral du over u is equal to t plus c. If I integrate this du over u, right, I'm integrating 1 over u, the antiderivative for this guy is a natural log. Now I'm going to do this once and only once. Notice that I actually wind up with a second constant of integration. And I have two of them at this point. I have a big C and I have a big D constant. So what winds up happening here, 1 over a times natural log of u, or absolute value of u, I'll have a D over a, and that's still just a constant. And what I want to do here is make life simple as possible here. Instead of dealing with two integration constants, I'm going to go ahead and bring that d over a to the other side of the equation. So I'll have c minus d over a. And I can go ahead and just call this guy a new constant. That's all this guy is. So effectively, I only had one integration constant, even though there were two different antiderivatives to compute. So this is a trick that a lot of the time textbooks will skim over, or they'll just take it on faith that you can kind of put pieces together and say, great, we have two integration constants, but let's just go ahead and consolidate them into one. And that's exactly what we do, and usually we just skip this step entirely and say that we don't need this capital D at all, and we just say, okay, take the integration constant from the integral on the left-hand side and consolidate it with the one on the right. And we will wind up with this as our starting point instead. So with that in mind, I will never do that again. I will only ever consolidate my my integration constants once and never worry about them again. There's just one constant to deal with. So quite frankly, if I put my substitution back, right, if I put u equal to ay plus b, back into the equation, then technically I'm done, right? I have an equation that tells me exactly what functions satisfy this differential equation. But usually what we wind up doing at this point is taking our implicit equation, so this is called an implicit solution, and we wind up solving this guy for the dependent variable y. So let's go a little further. Let's actually do this. So if I were to move any further forward, I would have to multiply through by the a, and I'd wind up with this. So at plus a times a constant c, which once again, we're going to go ahead and say that is going to be a new constant. So no problem there. If I want to keep getting at the a, then I have to exponentiate both sides, and I'll wind up with an absolute value of a times y plus b. And I'll have e to the at plus c1. But once again, this is just another constant. Right, I can separate the exponent because I have the same base here. Oh, geez. Because I have the same base. And I can call this guy c2. So let's go ahead and do that. This, we'll call that c2. So I'll wind up with c2. E to the at, and this has to equal the absolute value of ay plus b. Awesome. So problem now, we need to figure out how to get rid of the absolute value signs. Well, nobody really tells you what the inverse of this is because, well, honestly, there is no inverse function, right? It's actually not a one-to-one function. So what we actually wind up doing here is ask ourselves, what does the absolute value function do to anything? And the most it does is it adds a negative sign, right? It's either you get exactly what's inside at face value because it's a positive number, or it's a negative number and you have to slap a -1, a multiple of -1 on it. So if I drop the absolute value signs, that comes at a cost of picking up a plus or a minus sign. And that's all there is to it. And this guy we will call C3 because why not? And from here, it's just algebra. So ay is equal to c3 e to the at minus b, and y is going to be what happens when I divide through by an a. So this is, oh, you know the deal, c3 over a, e to the at minus b over a. And sure enough, if I go ahead and call this guy c4, well, no, I can go ahead and just call him a new constant altogether, a new name. So this will be y equals some constant times e to the at minus b over a. And that is an explicit representation and an analytic representation of what functions solve that differential equation at the top. Way back at the top here, this guy. And I can verify it, right? Let's check. What happens if I differentiate this? What is dy dt? Well, if I differentiate, this is d dt of constant times e to the at minus b over a. Well, the constant comes out for free. I differentiate the e to the at with a chain rule as a times e to the at, and, well, subtract off a 0, because derivatives of constants are 0. And what we wind up with is just a times k e to the at for the derivative of y with respect to t. Now, the thing that I also have to do is ask, what is a times y plus b? Well, a times y is k times e to the at minus b over a, and then I'll just add a b onto it. So what happens? Well, I get an a times a k e to the at minus a times b over a plus b, and we notice that these pieces sum together to give me a 0. So ak e to the at, and these two pieces are indeed identical. Therefore, so dy dt equals ay plus b as required. And that is exactly what it means to be a solution to this. And this equation here, this solution is valid for all k, all choices of k. All right, so whatever value, whatever real number you want to put in place for this constant k, this y of t will be a solution to the differential equation, right? Our verification was independent of that k value, right? The k came along for the ride, but it didn't play any part in the solution here. It didn't skew things at all. And when we have such a parameter in here, such a k, this is what is called a general solution to the differential equation, right? It's not dependent on anything, right? It's just telling you that there is an entire family of solutions, right? And that's exactly what's going on down here on this page of the lecture notes, that there is an entire family of solutions to this differential equation. And that's something that's maybe a little bit different than what we're used to in the algebraic setting, where there is one and only one solution to this this little linear equation. No, in this case, we actually get infinitely many solutions to one differential equation. And it turns out that these guys only depend on this multiple k that's sitting in front of the exponential term. So how about that? Now, to bring this full circle, if we had our dv dt equals, it was m times dv dt is minus mg minus gamma times v, which I can put into the correct form here, where we can use our result. We get minus g minus gamma over m times v. So in this case, the constant that's sitting in front of the v is the a term. So this is equal to minus gamma over m, and that would mean that the g term becomes the b, or minus g is b. And I can go ahead and use my solution from up here, right? So it's v of t is equal to some constant times e to the at, and that'll be minus a b over a. So in this case, it's k times e to the at, or e to the a is a minus gamma over m times t, and we'll subtract off a negative, so that's, so this will be minus, let's see, minus mg over gamma. And remember, we said as t goes to infinity, this guy will go to 0. So in other words, v of t goes to minus mg over gamma, and this was what we were calling the terminal velocity of our object. And we can specifically track what that quantity is if we have the parameters m, g, and gamma. Most of the time, these parameters are measured in a lab empirically or just through experiment empirically. And we wind up with a nice heuristic model for what we can expect from the behavior of a falling object with linear drag. All right, and I think this is a good spot to end the video for right now. We will talk in the next, should I? Yeah, I'll wait. We'll do this, we'll do